Um, Thank you very much. I wish I could have been there in person, but unfortunately it didn't work out that way. So I'm going to talk a little bit about some experiments we did on synthetic data set evaluation. I didn't put in the title, but this is in the context of machine learning. Um, so, so a little bit about what I'm talking about. Talk a little bit about what is synthetic data for ML? Why do you want to use it? What's a motivating scenario? Uh, some little discussion on the experiment setup, the data set that we use to evaluate our approach, and the experimental plans and results. So kind of the motivating scenario is, you have some ML problem you want to do. Maybe you want to build a classifier. Um, you only have a limited set of real data, and you would like to know when and how I can use synthetic data, and whether I should use synthetic data in my in training and testing my model. So some of the key questions you might have is, how good is your synthetic data compared to your real data on your model? And can you quantify that difference in how the model performs? And then where should I use the real data, and where should I use the synthetic data if I only have a limited amount of real data? As a proxy for this, for the real data that we care, the real data is CUI, so I can't show you any results on that. So we're using the Oxford 102 flower data set. So I'm going to be showing you lots of pictures of flowers today to demonstrate our approach. And then we use Dolly and a stable diffusion model to generate our synthetic data. So why would I be interested in using synthetic data? There are some, claims out there. People say that, synthetic data produces photorealistic data sets. And here are some examples. We have sort of a couple of actual photographs on the left, and some synthetically generated images on the right. And, just eyeballing it, it looks decent from the eyeball point of view. But we want to go beyond just the eyeball point of view and see how well it really works. Other claims might be that, using synthetic data is a waste of time if it doesn't work on our model, because it doesn't generalize the real data. But we'd like to, see how much that is true or not true. And also, we know that data collection, data labeling are, often the most time-consuming and expensive parts of a machine learning project. So what are some of the instances where I might use synthetic data, or some of the reasons? Could be data scarcity. The things that I want to operate on in the real world might be very difficult to get that data, expensive to collect it. The synthetic data can often be much cheaper to generate, so why not go ahead and use it? There could be data privacy issues if I'm using images of real people and I don't have their permission. There could be, PII included or other sensitive information that might prevent me from being able to use the real data. There could be class balancing reasons. So if when I'm training a model, ideally you want to have, similar numbers of images of all the different classes that I'm working with. And so I might use synthetic data to top off those classes. Label availability could be another problem. I can't find enough experts to label the real data I have. Domain randomization. We all know that if I'm using a classifier on, different types of vehicles in the desert, that classifier might not work very well if I go to like an Arctic region or something like that. And R&D speed up might be another time where we need to use synthetic data, because you can use the synthetic data to bootstrap your development work and get your experiment starting, and then replace your synthetic data as you go. All right, so here's just a little table of some different types of synthetic data. There could be, augmented data where I just take, cutouts of things. I paste a picture of a car in different environments to create my synthetic data. I could use like proxy objects, generative AI. which is what we'll be using in these experiments. Or you could be doing like soft simulation, we're using a game engine, or hard simulation, we're using a game-like simulation, but you've had experts validate the models in your simulation to make sure that they're representative of what you really care about. All right, so as I mentioned earlier, to demonstrate the technique, we'll be using the Oxford 102 data set, and here's a few examples from the data set. It has 102 different flowers in the data set, like magnolia, tree poppy, California poppy, primrose. There's 8,000 images in the data set, about 40, 80 per class, around 40, 80 images per class typically. The way we split it is from each class, we use 10 test images, 10 validation images, and then the rest of the data set for testing. Looking at the synthetic data sets we used, the first one is was Dolly generated images. So we have 4,000 of those. And here are some examples showing on the left, a couple images that were generated with Dolly, and on the right, sort of the same class of real data for like daffodil, primrose, Canterbury bells. These were generating using a prompt like a flower, whatever flower type you want in a location, and then we just add a loop that generated different combinations of target flower types and different background types. The advantage of this is it's very cheap. It's only a little over 1 cent an image to gather this sort of data, which is much cheaper than going and sending people out into the field to take flower pictures and get them labeled. And then since we're synthesizing, we have them pre-labeled, so that makes that a very cheap and attractive data set to use if we can get if they turn out to be as useful for training your model. The second data set we used was stable diffusion. This is a similar algorithm to the Dolly algorithm, but something that runs on your own machine. Generated about 3,000 of those, similar statistics in terms of how many we use per class. And again, you see some examples from the synthetic SD1.4 algorithm compared to their real counterparts. Similar prompt that was used to generate them, a whatever flower in a whatever location. And the cost is even cheaper than the Dolly images. It only costs your own electricity cost to do that. The model that we used for the experiments is a transfer learning based approach with the ResNet model as the base. So we did this in a sort of a 3-phase training. In the phase 1, we froze the weights in the ResNet model, the pre-trained model, and used a fairly high learning rate, 0.01. For 15 epochs, and then the later phase, we tune that to get a fairly high quality model. So the model would take an image at 224 by 224, and then predict a flower type from that. This was done with sparse categorical cross entropy to the loss function. And then in addition to the base classifier, we also have some experiments where we build a classifier to try to distinguish between real data and synthetic data as sort of a pre-experiment to evaluate the quality of a synthetic data set. Uses more or less the same architecture as our classifier, except replacing the final dense layer with a single output binary output saying, is it real or is it synthetic? So in our binary classification experiment, we used all the available data from both the real and synthetic for each of the set. We partitioned the data into an 80-10-10 split, 80% used for training, 10% validation, 10% test. We did an average, we're reporting an average of 5 runs with differently randomly selected splits. So we resplit it again and repeated the experiments. And what we would like to see on this experiment, if a synthetic data set is good, it's going to be harder to distinguish it from the real data. So lower is better on this test. If I get a 50% result on my real versus synthetic data set, that means that my trained model isn't able to distinguish real from synthetic. So we went and actually did that for the Dolly data set. We got a sort of 77%, 0.77 accuracy on trying to distinguish Dolly images from real images. And for stable diffusion, we got 0.855. So that suggests that in the following experiments where we go and actually look at how the performance of trained models using synthetic data versus real data perform, we're going to expect to see the Dolly data set performing consistently better. Here's a sort of in the lower left here, there's some examples of some, faults that we saw like from the stable diffusion. So like that picture in the left with the tiger, that was synthetic stable diffusion trying to generate a tiger lily. Then there was a Prince of Wales feather where it gave us an actual feather instead of there's a flower called the Prince of Wales feather, but it got confused and gave us an actual feather. Dolly does a little bit better. There's Dolly's tiger lily. It does. I found far fewer examples of these wildly off the wildly unexpected images. All right, so here is our first experiment looking at the differences in training quality, which we call the replacement set experiment. And in this experiment, we used a fixed amount of training data, and we gradually replace it with synthetic data. So we'll have training data that consists of a mix of real and synthetic data, and using real data for the validation in the test. And so what we would expect is that, we expect we know that the synthetic data is not as good as the real data since we are able to distinguish it. So as we increase the proportion of data that's synthetic, we should expect the quality of the results to go down, and that's what we see in the graph here on the right. So the upper curve, the blue one, is for Dolly. Going from on the left side is all real data for training, and the right side is all synthetic data for training. And so we go from about 77% accuracy on the model with real data to 30-ish% accuracy with the Dolly data. And we see also see that, as predicted, the Dolly data outperforms the synthetic data. So each of the points on here is actually an entirely different run of training a model on our training set, doing the validation, and doing the running the data on the test set. So there's quite a fair amount of computation at time to calculate this. So the next experiment we did, which was somewhat surprising, we call the augmentation experiment. And here we say we have a fixed amount of real data, and we want to ask the question, okay, so if we have this fixed amount of data, can we make the model better by adding additional synthetic data? So in this experiment, we use all our real data, and then we gradually add more and more synthetic data as we train and test the model. And the alpha here is, what fraction of the real data do we add in synthetic data? So again, the left-hand side at 0, that's all real data. And the right-hand side at 1, we're using sort of this double the amount of data, half real, half synthetic. What we see is that adding the additional synthetic data actually decreased our model accuracy. So even though we're using a larger training set, the quality of the model actually went down by adding the synthetic data. And part of the reason could be like those examples, like the tiger and the tiger lily, those types of things that are in the synthetic data that end up distracting from the quality of the model compared to the real data. But again, as you see, the Dolly data does still perform slightly better than the synthetic data, but the drop is not quite as large as it was in the replacement experiment. The last experiment we did was asking, okay, well, what if we use our synthetic data in the test experiment? So here we used a fixed amount of training data. We used real data for the validation, and then we used each of the two synthetic types for the test data, and then we compared that to the baseline. So we want to know, can we predict how well an all-real experiment is going to work with our synthetic data? And what we found is that the results using the synthetic data for testing were very far from what we get with the real data experiment. We also wanted to try sort of a different combination of models, or when changes happen to the data or changes happen to the model, how do the different scenarios react? And so to do that, we introduced mislabeling of the data. So the graph here shows what the model accuracy is as we deliberately mislabel a fraction of data. And as you expect with mislabeled data, you should expect the performance to go down. We do see them go down in a similar way between the Dolly and the real data and the stable diffusion in the real data. And again, we see the Dolly model do slightly better. So to summarize, going back to the three questions I started with, how good is your synthetic data compared to your model? So, even though, the pictures I showed you, visually looking at them, the synthetic data looks good from a human eyeball perspective, but we see that when we actually measure the performance, both the Dolly data and the synthetic data perform significantly worse than the real data, but that our binary classification test that we did at the beginning predicted that Dolly was going to do slightly better than the stable diffusion, and actually did do better. But the main takeaway here, more is not always better. The augmentation experiments show that even using synthetic data as additional data may not necessarily make your model better. And so you need to be prepared that kind of gives you more is not always better. And so you want to be prepared to measure the results. Quantify the difference. We did that initial experiment looking at Dolly and stable diffusion, predicted that Dolly was going to be better, and that's what we saw. Looking at sort of the test versus the training, we saw a dramatic difference between how the synthetic data performs for using it in training, and we did see that it worked if the cost of your synthetic data is significantly less than your real data, then you probably could justify the use of it based on what kind of drops we're seeing. But that when you have a choice between using your synthetic data for training versus test, you should invest your real data in the test when possible. Well, that's what I've got. Any questions?
Looks like we have a question here in the back. Yeah, very interesting talk. This is Brian Vickers from IDA. I'm very interested in the augmentation experiment because it's out of line with kind of my expectations, where we're typically seeing some kind of benefit in augmenting some of those data sets. I wonder if it's partially due to the fairly controlled nature of your data sets. So maybe if you removed one of those locations from the training data set and tried to see if you could use synthetic data to add those locations and then use that as your test data set. Is that kind of additional context or information potentially coming in from uh, synthetic data one of the reasons the augmentation might not be helping you here?
Well, again, the results you get are going to be dependent on the choice of the model and the choice of the data set. And I think that does sound like a very interesting to do more filtering based on the location. It actually did surprise us to see that degradation in performance. So, your mileage may vary depending on the data and how you generate it. Um, does that kind of get to your question? I think the most important thing is the approach and that these are the kind of experiments that you might want to be doing to test whether that holds true with your data set or not.
Any other questions? Yep, one more.
Hi, I had a similar question, kind of. Just wondering if you think you would find the same thing using noisier photographs or photographs with less simple, with more complex objects, for the augmentation experiment.
Um, I mean, that is a good question. I mean, I think some of the things like, like the animal tiger in the tiger lily one or kind of introducing noise in the data. Are you thinking more noise in the background?
Sorry. Or I guess more decision criteria in the object in the photograph, for example. So flowers are simple objects, and angles for pictures of flowers tend to be kind of like straight on or at a particular angle. So either the angle that the photograph of the object is taken at, or kind of just additional noise like that, or distance, something.
Yeah, I mean, one of the synthetic types that we wanted to do that we haven't had time to get to yet would be like using like a 3D, like a game engine type thing and 3D models of flowers. And that would give you the ability to take pictures of your objects from different angles.
Thank you.
Okay, let's go ahead and thank Dr. Hansen again.